Greetings. Now, if you've ever wondered what the Reynolds number really is or how to calculate it, keep watching this video. The Reynolds number is a way of characterizing a fluid flow. Now, you could have a fluid flowing through a pipe. So maybe you got water through a pipe, something like that. And depending on the size of the pipe and the temperature of the water and a number of other things, um, w- we will be able to calculate this Reynolds number, sometimes denoted as RE. There are a few other ways of denoting it. But what really is this thing? Well, it's kind of like taking the temperature of someone's body. If it's at a certain temperature that's normal, then you know certain things are not happening. If they have a fever, you know that there are some problems. If they're too low, maybe there's hypothermia. Same thing with the Reynolds number. If it's at a certain level, then you know one kind of flow is happening. If it's at another level, you know a different kind of flow is happening. If it's in between, it's something called transition. We'll get to that in a second. So the Reynolds number uh, is actually a ratio between two forces. There are the inertial forces of the water, and then there's the forces of the things trying to go through. So in this case, it's the pipe. If there happens to be an object in the middle, maybe a post or something like that, then this post will also have uh, forces that are pushing back on it. Um, Sometimes there's drag and so on. And these are shear forces along the edges and other types of forces that are pushing back. So the Reynolds number is a ratio between the inertial forces of the fluid that are trying to move in a certain direction versus the viscous forces that are kind of pushing back against it. Now, there are other forces involved here in this kind of flow, but this Reynolds number hits a couple of the big ones, the inertial forces over the viscous forces. And again, this Reynolds number here can help us figure out what kind of flow is happening with this particular setup. Now, it's dependent on a variety of things. So, if we actually added up all the inertial forces up top and divided them by the viscous forces, it might be a little bit complicated, but many terms cancel, and we end up with the density of the fluid times the relative velocity of the fluid times this characteristic length. We'll talk more about what that characteristic length is in a bit. And we divide it by the dynamic viscosity of the fluid. If you notice, we can take the density and the dynamic viscosity and note that the kinematic viscosity, nu, is equal to the dynamic viscosity divided by the density. And we can take that, plug it in here, and we get the velocity of the flow times this characteristic length, all divided by the kinematic viscosity. Now, if possible, I would recommend using this formula, especially if you know exactly what the fluid is and so on, because the kinematic viscosity is well documented for a particular fluid at a particular temperature. So let the tables give you this instead of having to divide this whole thing all the time and dealing with the unit conversions and so on. That can be kind of tricky and problematic. So this is a simpler take advantage of it when you can. Speaking of units and dimensions, let's look at what we have here. We have density, which is mass per unit volume, and volume is length cubed, so some kind of cubic length, cubic centimeters or something like that. And then we have velocity, which is length per unit time, and then we have some length over here, so that's a length. Then we divide it by the dynamic viscosity, which is actually stress times time. Oof. Okay, so stress is a force over an area. And so a force is a mass times acceleration. Acceleration is length per time squared. So here's my force, mass times acceleration. Divide that by my length squared. I've got force over area, and then that's my stress, and then I multiply it by time. So this looks really, really messy. Well, we're going to cancel this time that's on the bottom with this time that's on the bottom, and this time's on the bottom, and we're going to cancel it with that one. So the times actually cancel out. Here's the mass up here. Those cancel out. Well, this is length cubed on the bottom. This is length squared that's on the bottom, which means it brings it up on top. So I cancel that out with that. And then this length cancels out with the rest of that. And then this one's on the top and this one's on the bottom. So guess what we end up with? We end up with a dimensionless number. So it's not like a temperature of a body in this way. It has no dimensions, has no meaning in that way, but it has other meanings. But this is exactly what we would expect to get when we have forces divided by forces. We expect to get a dimensionless number. Next, I want to address the characteristic length, this thing right here. This can be a variety of things. If you have a pipe flow like this and the pipe is full, then it's simply the diameter of the pipe. One of the biggest confusions is that this length has nothing to do with the length of the pipe. I got that all confused when I was first learning this. This length, how long it travels, has nothing to do with the Reynolds number. Okay, this is a characteristic length. It might be the diameter of the pipe. If the pipe is rectangular, there's a formula for that. If the pipe is not full, maybe it's just an open channel, whether it's an airfoil or a golf ball going through the air. This characteristic length is sometimes the most difficult thing to track down. Finally, what does this all mean? Well, if you have a high Reynolds number, you end up with turbulent flow. Turbulent flow can be desired when you want mixing, if you're trying to have heat transfer, if you're trying to make a mixture of things. But if you are trying to just move stuff from one place to the other, you want laminar flow. Now, if you turn on your kitchen sink to a very low flow, you very often will see a very nice crystal clear flow. But as you turn up the speed, increasing this number, you'll increase the Reynolds number and you'll see turbulent flow. In between, you'll see transition. And you'll see that as well in your kitchen faucet. You will see that it starts to wobble a little bit, and that's the transition flow. Thank you for watching, and I hope this helped. Please send feedback if you have any suggestions on how this could be improved.